March 17, 1991. Somewhere over the desert expanse of southern Iraq, 30,000 feet above a landscape pockmarked by burning oil wells and the remnants of shattered Republican Guard divisions. The cockpit of an E-3 Sentry banked gently through thin air, its four Pratt& Whitney turbofans maintaining a steady 360 miles per hour as the aircraft traced an invisible racetrack pattern along the Saudi border. Behind the flight deck, in a dimly lit cabin crammed with 14 operator consoles and humming with the low whir of cooling fans, Technical Sergeant Mike Navratil pressed his headset closer to his ear and watched as dozens of small triangular symbols crawled across his green phosphor radar display. Each symbol represented an aircraft, a radar return plucked from the electromagnetic chaos below by the massive rotating dome spinning 6 revolutions per minute 11 feet above the fuselage. Navratil had been on station for 6 hours, coordinating strike packages, managing tanker rendezvous points, and keeping close watch on the Iraqi Air Force units that still dared to venture into contested airspace. He was exhausted, but adrenaline sharpened his focus. At 0340 hours, a new contact blinked onto his screen, 70 nautical miles northeast, climbing fast from an airfield near Basra. Seconds later, the identification friend or foe interrogator confirmed the hostile designation. Navratil keyed his microphone and calmly passed vectors to a pair of F-15C Eagles loitering 40 miles to the west. Within 4 minutes, one of those Eagles locked onto the Iraqi MiG-29 and fired an AIM-7 Sparrow missile. The MiG disintegrated in midair, its pilot never knowing that his takeoff had been tracked, his altitude calculated, and his fate sealed by a radar system he could neither see nor jam, operating from an altitude and range his own ground controllers could not match. It was the 38th confirmed air-to-air kill of Operation Desert Storm coordinated by an AWACS crew, and it would not be the last. This mission, repeated hundreds of times across 43 days of sustained air operations, represented the culmination of a technological revolution that had been unfolding quietly since the mid-1970s. For over a decade, Soviet air defense planners had constructed an elaborate architecture of early warning radars, surface-to-air missile batteries, and fighter intercept doctrine predicated on a single unshakable assumption: that air battles would be decided by the side with the fastest jets, the longest-range missiles, and the most robust ground radar network. Soviet ground-controlled intercept doctrine relied on a vast web of P-12 spoon rest and P-35 bar lock radars deployed across Eastern Europe and the western military districts of the Soviet Union, feeding data into centralized command bunkers where controllers would vector MiG-23, MiG-25, and Su-27 interceptors toward inbound NATO strike packages. Soviet confidence in this system was immense. They had spent billions of rubles hardening radar sites, training intercept officers, and refining procedures designed to funnel enemy aircraft into engagement zones where integrated air defenses could achieve decisive kill rates. In classified assessments circulated through the Soviet General Staff and captured years later by Western intelligence, Soviet Air Defense Forces Command estimated that NATO penetration raids would suffer attrition rates exceeding 15% per sortie if forced to operate without air superiority. They believed the sheer density of their radar coverage, combined with numerical superiority in interceptors, would create an impenetrable defensive shield. But that confidence rested on a critical blind spot. Soviet planners had designed their doctrine for an era when early warning meant ground-based radars scanning fixed sectors of sky, when battle management meant voice communication over vulnerable radio links, and when the side that detected an enemy first gained perhaps 90 seconds of warning. They had not planned for an adversary who could see everything, everywhere all at once, from an altitude their interceptors struggled to reach, with a persistence their own radar networks could not sustain. On March 24, 1977, a Boeing 707 with an unmistakable 30-foot rotating radar dome mounted on its back touched down at Tinker Air Force Base, Oklahoma. The arrival was quiet, almost routine, noted in a handful of aviation trade journals but absent from front-page headlines. Yet that landing marked the operational debut of a weapons system that would fundamentally rewrite the mathematics of air combat and render obsolete nearly every assumption Soviet air defense strategists had codified in their doctrine manuals. The E-3 Sentry, officially designated as the Airborne Warning and Control System, was not a fighter, not a bomber, not a reconnaissance platform in the traditional sense. It was something entirely different. A flying command post capable of detecting, tracking, and managing hundreds of airborne contacts simultaneously across a surveillance bubble extending more than 250 miles in every direction. The aircraft's heart was the Westinghouse AN/APY-1 pulse-Doppler radar, a technological marvel that used digital signal processing to discriminate moving targets from ground clutter, allowing operators to detect low-flying aircraft over land, an achievement that had eluded earlier airborne radar designs. Unlike ground-based radar systems, which were limited by the curvature of the Earth and terrain masking, the E-3 operated at altitudes above 29,000 feet, giving it a radar horizon unmatched by any static installation. A single AWACS aircraft orbiting over West Germany could surveil airspace from the Baltic Sea to the Austrian border, tracking Soviet fighters taking off from bases in East Germany, Poland, and Czechoslovakia before they even reached cruising altitude. The radar's Beyond the Horizon pulse mode extended detection range to nearly 400 miles for high-altitude targets, creating a surveillance umbrella so vast that NATO air commanders could observe the entire theater of operations in real time. The numbers were staggering, and they were not classified for long. The E-3's rotating antenna spun at 6 revolutions per minute, transmitting pulses across multiple frequency bands while simultaneously processing returns through an onboard computer system based on IBM's 4Pi architecture. This computer, running software written in the jovial programming language, could track up to 600 airborne contacts simultaneously, assigning each a unique identifier, calculating its speed, heading, altitude, and rate of climb, and displaying this information on consoles manned by 13 mission specialists seated in the cabin behind the cockpit. These specialists were not passive observers. They were weapons controllers, battle managers, and intelligence analysts, each responsible for a sector of the surveillance picture, and each capable of directing friendly fighters, strike aircraft, and support platforms through a secure tactical data link known as Joint Tactical Information Distribution System, or JTIDS. This system, later upgraded to support Link 16 digital communication protocols, allowed the E-3 to transmit targeting data directly to F-15s, F-16s, and other coalition aircraft, creating a networked battlespace where every friendly asset operated from a common operational picture. Soviet air defense officers, monitoring NATO exercises from listening posts along the Iron Curtain, began reporting anomalies in NATO fighter behavior as early as 1979. Intercepted radio communications showed that NATO fighters were responding to threats with uncanny speed and precision, vectoring toward Soviet aircraft long before ground radar systems detected them, maneuvering into optimal firing positions with a coordination that suggested real-time centralized control. What the Soviets were witnessing was the operational manifestation of AWACS capability, but they initially struggled to understand its full implications. The E-3 was not just a radar platform. It was a flying intelligence node capable of fusing data from multiple sensors, including electronic support measures that passively detected and geolocated enemy radar emissions, allowing AWACS operators to build a comprehensive electronic order of battle without transmitting a single pulse. The aircraft's secondary surveillance radar interrogated the identification friend or foe transponders installed in NATO aircraft, instantly distinguishing between friendly, neutral, and hostile contacts, and eliminating the fratricide risk that had plagued earlier air battles. Its communications suite included high-frequency, very high-frequency, and ultra-high-frequency radios, secure satellite links, and encrypted data channels that connected the AWACS directly to theater air operations centers, fleet command posts, and even national command authority. In a crisis, the E-3 could relay targeting information not only to fighter pilots, but also to the President of the United States and the Secretary of Defense, ensuring that decision-makers had real-time situational awareness of unfolding air operations. This capability transformed the E-3 from an early warning system into a command and control backbone for the entire joint force, a platform that allowed a single aircraft to orchestrate an air campaign involving hundreds of sorties across thousands of square miles of contested airspace. By 1984, when the 34th and final USAF E-3 was delivered, the United States had deployed 27 sentries to Tinker Air Force Base and positioned 4 more in the Pacific Theater at Kadena Air Base in Okinawa and Elmendorf Air Force Base in Alaska. NATO, recognizing the strategic value of the platform, ordered 18 E-3A aircraft, which entered service at Jelenkirchen Air Base in West Germany beginning in January 1982. The message to the Warsaw Pact was unmistakable. NATO now possessed an eye in the sky that could observe Soviet air operations in real time, from takeoff to landing across the entire European theater. If you appreciate discovering Cold War secrets hidden for decades, consider subscribing for future declassified revelations. Soviet military intelligence began compiling detailed assessments of AWACS capabilities throughout the 1980s, and those documents, declassified decades later, reveal a mixture of grudging respect and mounting alarm. A report prepared by the Soviet Air Defense Forces main staff in 1986 concluded that the deployment of NATO AWACS represented a qualitative shift in the correlation of forces, and warned that Soviet air operations would face unprecedented disadvantage in any scenario involving sustained air combat over Central Europe. The report noted that while Soviet forces maintained numerical superiority in fighters and interceptors, NATO's airborne early warning capability conferred a decision advantage measured not in minutes, but in the critical seconds that determined who fired first. Soviet planners calculated that NATO fighters directed by AWACS could achieve first-look, first-shot opportunities in more than 70% of engagements, a kill probability that rendered Soviet numerical advantages meaningless. The report recommended urgent development of countermeasures, including dedicated electronic warfare aircraft designed to jam AWACS radar frequencies, long-range air-to-air missiles capable of targeting AWACS platforms at standoff ranges, and accelerated deployment of the Bereev A-50 mainstay, the Soviet Union's own airborne early warning aircraft. But the A-50, based on the Ilyushin Il-76 transport and equipped with a rotating Liana radar system, did not achieve initial operational capability until 1989, more than a decade after the first E-3 entered service. Even then, Soviet AWACS capability lagged significantly behind its American counterpart. The A-50 could track only 50 to 70 targets simultaneously, compared to the E-3's 600. Its radar range was shorter, its endurance limited by fuel capacity and crew rest constraints, and its command and control systems lacked the digital data link architecture that made the E-3 so effective. Most critically, the Soviet Union built only 40 A-50 aircraft, a force insufficient to provide continuous coverage over the vast expanse of Soviet airspace, let alone support offensive air operations over NATO territory. The true measure of AWACS dominance came not in Cold War exercises but in actual combat, and the proving ground was the skies over Iraq and Kuwait during Operation Desert Storm. On January 17, 1991, at 0238 hours local time, coalition strike aircraft began crossing into Iraqi airspace, initiating an air campaign that would ultimately involve more than 120,000 sorties over 43 days of sustained operations. From the opening minutes of the war, E-3 Sentry aircraft were airborne, orbiting in carefully choreographed patterns over Saudi Arabia, the Persian Gulf, and Turkey, providing uninterrupted radar coverage of Iraqi airspace. The AWACS mission planners had divided the theater into surveillance sectors, assigning each E-3 a designated orbit that ensured overlapping radar coverage and eliminated blind spots. Throughout the campaign, AWACS aircraft flew 379 missions and logged more than 5,000 hours of on-station time, maintaining an average of 2 to 3 aircraft airborne at all times, each monitoring a slice of the battlefield and feeding data into the Combined Air Operations Center located deep within a hardened bunker in Riyadh. The operational tempo was relentless. AWACS crews worked in shifts, coordinating strike packages, managing air refueling tracks, directing combat air patrols, and tracking Iraqi aircraft attempting to flee to Iran or engage coalition forces. The E-3's radar picture became the authoritative source of air situational awareness for the entire coalition, and every major tactical decision from target selection to abort criteria was informed by data provided by AWACS operators. The results spoke for themselves. Coalition air forces achieved total air superiority within the first 72 hours of the campaign, a feat unprecedented in modern warfare. Iraqi fighters that attempted to engage coalition aircraft were systematically destroyed, often before their pilots realized they were being tracked. Of the 41 confirmed air-to-air kills recorded during Desert Storm, 38 were directly enabled by AWACS queuing, with E-3 controllers providing early warning, precise target coordinates, and real-time tactical guidance to F-15C and F-16C pilots. The lethality was not just a function of superior aircraft or missiles, although those certainly played a role. It was the result of information dominance. AWACS operators could see Iraqi fighters taking off from their bases, predict their flight paths, and vector coalition fighters into optimal intercept positions long before the Iraqis detected any threat. This capability turned air combat from a contest of speed and maneuverability into a methodical execution, where the side with better situational awareness won before the merge. Coalition strike packages, guided by AWACS controllers, penetrated Iraqi airspace with near impunity, delivering precision-guided munitions on targets ranging from command bunkers to radar sites to Scud missile launchers, all while maintaining coordination with supporting assets like EA-6B Prowler electronic warfare aircraft and KC-135 aerial refueling tankers. The complexity of these operations would have been unmanageable without the centralized battle management provided by the E-3. AWACS controllers acted as aerial traffic controllers, deconflicting flight paths, managing altitude blocks, and ensuring that hundreds of coalition aircraft operating in confined airspace never collided or interfered with each other's missions. This level of coordination was only possible because every aircraft in the theater was visible on the AWACS radar picture, and every pilot could receive real-time instructions via secure data link. But perhaps the most remarkable statistic from Desert Storm was this: coalition air forces recorded 0 air-to-air losses. Not a single coalition fighter was shot down by an Iraqi interceptor during the entire campaign. This achievement was not luck. It was the direct result of a battle management architecture built around AWACS, a system that ensured coalition fighters always had superior situational awareness, always engaged from positions of advantage, and always knew the location of threats before those threats could prosecute an attack. Iraqi Air Force commanders trained in Soviet air combat doctrine and equipped with Soviet-built MiG-29 and Mirage F-1 fighters found themselves outmatched not because their aircraft were inferior, though many were, but because they were operating blind. Iraqi ground-based radar networks, subjected to relentless suppression of enemy air defenses campaigns, were degraded within hours of the war's start, leaving Iraqi pilots dependent on cockpit radars with limited range and no support from airborne early warning platforms. Meanwhile, coalition pilots operated within a networked battle space where every aircraft's position, every threat, and every opportunity was visible in real time on their cockpit displays, updated continuously by AWACS data links. The psychological impact on Iraqi pilots was profound. Intercepts of Iraqi Air Force communications revealed confusion, disorientation, and eventually despair, as pilots realized they were being tracked, targeted, and destroyed by an enemy they could not see and could not evade. Many Iraqi pilots chose to flee to Iran rather than face certain death, resulting in the defection of more than 100 Iraqi aircraft, including some of the Air Force's most advanced fighters. Those who stayed and fought were hunted with clinical efficiency, their every move anticipated, their every maneuver countered, their fate determined by a radar system orbiting 30,000 feet above the battlefield, beyond the reach of Iraqi air defenses. The E-3's impact extended far beyond air-to-air combat. In support of ground operations, AWACS provided direct intelligence on Iraqi helicopter movements, allowing coalition forces to interdict troop transports and attack helicopters before they reached the front lines. The E-3's maritime surveillance mode, leveraging the radar's beyond-the-horizon pulse capability, tracked Iraqi naval vessels attempting to lay mines in the Persian Gulf, providing targeting data to coalition naval forces and ensuring safe transit lanes for amphibious assault ships and logistics vessels. AWACS also played a critical role in combat search and rescue operations, coordinating the recovery of downed coalition aircrews by maintaining continuous surveillance over contested areas and directing rescue helicopters along routes cleared of enemy threats. In every phase of the campaign, from the strategic air offensive to the ground war that followed, the E-3 Sentry functioned as the central nervous system of coalition air power, translating raw sensor data into actionable intelligence and enabling a level of operational tempo that overwhelmed Iraqi defenses. The data collection capability of the E-3's radar and computer systems allowed the entire air war to be recorded in unprecedented detail, providing historians and military analysts with a complete picture of every sortie, every engagement, and every tactical decision. This archive, still partially classified, remains one of the most comprehensive records of air combat ever compiled, a testament to the revolution in military affairs that AWACS represented. Soviet military observers, monitoring Desert Storm from Moscow and through intelligence channels in Baghdad, were forced to confront an uncomfortable truth. The air campaign had validated NATO's investment in airborne early warning and control, demonstrating that information dominance could offset numerical inferiority and technological parity. Soviet Air Force doctrine, which emphasized mass formations of interceptors supported by ground-based radar networks, was revealed as obsolete in an era where a single AWACS aircraft could track every aircraft in a theater and direct precision strikes with near-zero losses. The lessons were bitter. Soviet air defense planners had assumed that NATO strike packages would suffer attrition rates high enough to make sustained air operations prohibitively costly. Instead, coalition forces had flown 120,000 sorties with a loss rate below 0.1%, a figure so low that it challenged every assumption underpinning Soviet air defense strategy. The implications extended beyond tactical aviation. If NATO could achieve total air dominance over a modern integrated air defense system like Iraq's, then Soviet air defenses, despite being more sophisticated in some respects, would face similar challenges in any conflict with NATO. The E-3 Sentry had not just enabled victory in Desert Storm. It had fundamentally altered the calculus of air warfare, demonstrating that the side that sees first tracks continuously and coordinates seamlessly controls the battlespace, regardless of the number of fighters or missiles the adversary deploys. The technical specifications that enabled this dominance were both remarkable and in many cases deliberately engineered to exceed Soviet capabilities. The Westinghouse AN/APY-1 radar operated in S-band frequencies, transmitting pulses that could penetrate weather, detect low observable targets, and discriminate between aircraft and ground clutter with a fidelity no Soviet radar system could match. The radar's pulse-Doppler mode used Doppler frequency shifts to calculate target velocity, allowing operators to distinguish between stationary objects and moving aircraft even in dense electromagnetic environments. The radar's antenna, a passive electronically scanned array housed within the rotating dome, used phase shifters to focus radar energy into a narrow beam that could be electronically steered in elevation, enabling the radar to scan from ground level to altitudes exceeding 100,000 feet without mechanical movement. This gave the E-3 the ability to simultaneously track aircraft flying at treetop level and bombers cruising at the edge of the stratosphere, a capability that no ground-based radar could replicate due to horizon limitations. The radar's maximum detection range for airborne targets varied with altitude and radar cross-section, but unclassified Air Force fact sheets confirmed ranges exceeding 250 miles for low-flying aircraft and approximately 400 miles for high-altitude targets, creating a surveillance bubble that covered more than 500,000 square miles of airspace. Power requirements for the radar and mission systems were immense, necessitating electrical generators mounted in each of the E-3's 4 engines, producing a combined output of 1 megawatt. This electrical capacity supported not only the radar but also the aircraft's communication suites, computer systems, operator consoles, and environmental control systems necessary to keep mission equipment within operational temperature ranges. The rotating dome itself was an engineering marvel, a 30-foot diameter structure weighing approximately 1,800 pounds, held 11 feet above the fuselage by 2 hydraulic struts, and tilted slightly forward to reduce aerodynamic drag. The dome rotated continuously during flight, completing 6 revolutions per minute, driven by a hydraulic system uprated to pressures of 5,000 pounds per square inch specifically to handle the mechanical stresses of sustained rotation at altitude. Inside the unpressurized dome, cooling was provided by bleed air from the engines, supplemented by fluorocarbon-based cold plates that dissipated heat generated by radar electronics. The engineering challenges of maintaining stable rotation, preventing ice accumulation, and ensuring reliable power transmission to the spinning antenna were formidable, and Boeing's successful integration of these systems represented a significant aerospace achievement. The E-3's airframe, a modified Boeing 707-320B, was selected for its proven reliability, range, and payload capacity. The aircraft's 4 Pratt & Whitney TF-33PW100A turbofan engines, each producing 20,500 pounds of thrust at sea level, provided the power necessary to carry the radar dome, mission equipment, and crew to operational altitudes exceeding 29,000 feet, where the thin air and reduced atmospheric interference maximized radar performance. Endurance was a critical performance parameter, and the E-3 was designed for long-duration missions. Unrefueled endurance exceeded 8 hours, sufficient for extended surveillance missions over NATO airspace, but air-to-air refueling capability, provided by a receptacle compatible with KC-135 and KC-10 tanker aircraft, extended on-station time indefinitely. During Desert Storm, some AWACS missions exceeded 14 hours, with crews rotating through rest areas equipped with bunks and a small galley to manage fatigue during extended operations. The aircraft's range, exceeding 5,000 nautical miles, allowed AWACS aircraft based at Tinker Air Force Base to deploy anywhere in the world with a single refueling stop, and NATO AWACS based at Jalenkirchen could patrol from the Baltic Sea to the Mediterranean without returning to base. This global reach meant that AWACS coverage could be rapidly deployed to crisis regions, providing theater commanders with airborne early warning within hours of a decision to intervene. The crew composition reflected the E-3's dual role as both surveillance platform and battle management node. The flight crew consisted of 4 personnel: aircraft commander, pilot, navigator, and flight engineer, responsible for flying the aircraft, managing fuel and systems, and coordinating with air traffic control. The mission crew varied from 13 to 19 specialists, depending on mission requirements, and included radar operators, weapons controllers, communications managers, electronic warfare officers, and intelligence analysts. Each operator sat at a console equipped with multiple display screens showing radar returns, data link information, and tactical overlays, with controls that allowed them to interrogate specific contacts, assign targets to friendly fighters, and communicate via secure voice and data channels. The integration of human judgment with automated tracking algorithms created a battle management capability that combined the processing power of computers with the tactical intuition of experienced operators, a synergy that Soviet air defense systems, which relied more heavily on rigid procedural responses, struggled to match. Upgrades throughout the 1980s and 90s continuously enhanced the E-3's capabilities, ensuring that the platform remained relevant as threats evolved and technology advanced. The Block 3035 modification program, completed between 1987 and 2001, added electronic support measures that passively detected and geolocated enemy radar emissions, providing AWACS operators with a detailed electronic order of battle without revealing the E-3's position through radar transmissions. The program also installed the Joint Tactical Information Distribution System Class 2H, enabling Link 16 data link capability that allowed the E-3 to share tactical information with a broader range of NATO and coalition platforms. Global positioning system receivers were integrated, improving navigation accuracy and enabling precise georegistration of radar contacts. Onboard computers and software were overhauled to accommodate these new systems and to provide additional processing power for future enhancements. The Radar System Improvement Program, a joint U.S.-NATO development effort, replaced obsolete transistor-transistor logic and emitter-coupled logic components with modern off-the-shelf computers and added pulse compression to the pulse-Doppler radar mode, significantly improving detection performance against low radar cross-section targets. These hardware and software modifications enhanced the E-3's ability to detect and track stealth aircraft, cruise missiles, and other emerging threats that earlier radar designs struggled to identify. The RSIP upgrade, completed across the USAF and NATO fleets by 2006, ensured that AWACS remained effective against adversaries investing in reduced observability technologies. The psychological and doctrinal impact of AWACS extended far beyond its technical specifications. Soviet and later Russian military strategists recognized that the E-3 represented a paradigm shift in air warfare, one that invalidated decades of investment in interceptor fleets and ground-based radar networks. The traditional Soviet model of air defense, which relied on dense overlapping radar coverage feeding centralized command posts that vectored interceptors toward detected threats, assumed that both sides would operate from similar informational baselines. AWACS shattered that assumption. NATO forces could detect, track, and engage Soviet aircraft long before Soviet ground controllers even knew NATO fighters were airborne. This asymmetry meant that Soviet interceptors, no matter how fast or heavily armed, would be reacting to threats rather than prosecuting attacks, a defensive posture that guaranteed inferior outcomes in air combat. Soviet attempts to develop countermeasures, including long-range air-to-air missiles designed to target AWACS platforms, were hampered by the E-3's operational altitude, its escort by fighter aircraft, and its ability to operate well behind friendly lines, making it a difficult target to engage. Soviet doctrine called for dedicating interceptors specifically to hunt AWACS aircraft, recognizing that destroying or jamming these platforms would blind NATO air operations. But in practice, getting close enough to an AWACS to engage it required penetrating layers of fighter cover and surviving the very networked air defenses that AWACS enabled. The few exercises where Soviet aircraft attempted to simulate AWACS intercepts revealed the difficulty of the task. And by the late Cold War, Soviet planners had largely concluded that neutralizing NATO AWACS capability would require coordinated strikes using long-range cruise missiles or unconventional means, options that carried significant escalation risks. The E-3 Sentry's legacy extends into the 21st century, where it continues to serve as the backbone of NATO airborne early warning despite the airframe's age, and the pending introduction of the Boeing E-7 Wedgetail as a replacement. AWACS aircraft have supported nearly every major NATO and U.S. military operation since Desert Storm, including the enforcement of no-fly zones over Bosnia and Iraq throughout the 1990s, the air campaign during Operation Allied Force over Serbia and Montenegro in 1999, and sustained operations over Afghanistan and Iraq following the September 11th terrorist attacks. In each of these conflicts, the E-3 provided the same capabilities that defined its role in Desert Storm: persistent surveillance, real-time battle management, and seamless coordination of air operations across coalition forces. NATO AWACS aircraft played a critical role in Operation Eagle Assist, the alliance's first invocation of Article 5, patrolling American airspace in the weeks following the September 11th attacks to augment NORAD's air defense coverage. More recently, NATO E-3s have conducted continuous surveillance missions over Eastern Europe in response to Russian military activity near Ukraine, monitoring airspace over Poland, Romania, and the Baltic states, and providing early warning of any incursions into NATO airspace. These missions, flown daily since February 2022, demonstrate that the fundamental mission of AWACS, seeing first and maintaining situational awareness, remains as relevant today as it was during the Cold War. The story of the E-3 Sentry is not merely one of technological innovation, though the engineering accomplishments were significant. It is a story of strategic vision, of recognizing that future wars would be won not by the side with the most weapons, but by the side with the best information. Soviet air defense commanders learned this lesson the hard way, watching as NATO exercises demonstrated capabilities they could not match, and seeing their doctrine rendered obsolete by a single platform that could see everything everywhere all at once. The E-3 turned the sky into a transparent battlespace, where every aircraft, every movement, every decision was visible in real time to controllers who could direct assets with precision measured in seconds and meters. In the calculus of air warfare, where success depends on firing first, maneuvering into advantage, and coordinating complex operations across vast distances, the side that sees first controls the battle. AWACS proved that information dominance is air dominance, that technological superiority in sensors and battle management systems translates directly into operational success, and that adversaries who underestimate the value of situational awareness do so at their peril. Soviet commanders trusted their ground radar networks, believed their numerical superiority would prevail, and assumed NATO's investment in airborne early warning was a defensive measure. They were wrong. The E-3 Sentry was an offensive weapon, one that allowed NATO to project power, sustain operations, and achieve air superiority in environments where attrition should have made victory impossible. It revealed that the future of warfare belonged not to those with the fastest jets or the longest-range missiles, but to those who could see the battlefield entire, process information faster than the enemy, and act on that knowledge before the adversary realized the battle had begun. In a world where seconds decide survival, the E-3 demonstrated that the side which sees first wins, and that controlling information is controlling the war itself. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink.